Okay, welcome back, ladies and gents. Topic 2.7, Vesper and hybridization theory. We're first going to look at the theory of hybridization and orbital hybridization and how we can use this to describe the bonds that we observe in certain molecules. Let's start with carbon here. As you all know, the electron configuration for carbon is 1s2, 2s2, 2p2, total of 6 electrons, and in the outermost energy level, which is this 2s and 2p, there are 4 valence electrons. If we were to make a molecular orbital diagram right here for an unhybridized carbon, meaning that none of the s and p orbitals are mixing, they are all each separate orbitals, we would see that we have 2 electrons starting down here in the 1s orbital, because we fill electrons in based on lower energy levels, and then we have to pair the electron up before we can move up to the next orbital. So that takes care of these 2 1s electrons, and then we have 2 more electrons in the 2s orbital, and then we have 2 electrons in the 2p orbital. Okay, and remember, we have to separate the electrons out before we can double them up. You don't have to know how to make these orbital diagrams, we're just going to use it here as an example, okay? And also, as a reminder, the energy of each of these electrons increases as we get to higher level orbitals. Now remember, you guys all know that carbon has 4 valence electrons. And if you were to make the Lewis dot diagram for carbon, you would see that each of those 4 valence electrons are unpaired. So technically, carbon, or not technically, it can make 4 bonds. This is a little bit of a discrepancy. With what we see here, carbon can make 4 bonds because there's 4 unpaired electrons. However, in this orbital diagram, there are only 2 unpaired electrons. So, how do we account for this discrepancy? Scientists came up with this theory that the orbitals must be hybridizing, or they must be mixing together, so that they achieve an orbital that's lower in energy, but can account for the fact that the number of observed bonds actually do occur. And this is where hybridization theory comes in, and we go into sp hybrid orbitals. What are sp hybrid orbitals? Sp hybrid orbitals occur when the s orbital mixes with the p orbital, okay? And remember, there are 3 different types of p orbitals, okay? So what scientists said must be happening is that this s orbital right here is mixing with these 3 p orbitals to make what's known as an sp hybrid orbital, okay? So we still have the 1s orbital here with its 2 electrons. Those 2 electrons are not going to be involved with any mixing because these are core electrons right here. S and p hybridization only occurs with the valence electrons, and carbon only has 4. So these s and p orbitals are mixing to form an sp hybrid, so that there are now 4 spaces up here, okay? Because this s orbital is mixing with these 3 p orbitals, and now we have an sp mixed hybrid orbital with 4 spaces, okay? And if we go in to fill the molecular orbital diagram now with the 6 total electrons, we have 2 in this 1s orbital, and then we have 4 more remaining to put here. And this represents the new valence shell with 4 unpaired electrons, which matches what we see carbon doing. Okay, so that's sp hybridization there. It's when the s and p orbitals mix together to form a hybrid orbital, so that we can describe and accurately talk about how bonds actually occur in nature. Right? There are in fact 3 different ways that s and p orbitals can mix. The first way the s and p orbitals can mix is when you have an sp3 hybridized orbital. This occurs when the s orbital mixes with all 3 p orbitals, okay? So we're going to mix the s with all 3 p orbitals, and this makes an sp3 hybrid orbital, okay? We'll talk about bond angles a little bit later, but when sp3 hybrid orbitals come together, they have a 109.5 degree bond angle. So if you look at this image right here, this is one sp3 hybridized orbital, this is another sp3 hybridized orbital, and then another one. Okay, so we have 4 lobes here to represent the 4 orbitals mixing. And when that happens, they have to arrange themselves in such a way that these electrons over here are as far away from each other as possible by Coulomb's law, and you get a 109.5 degree angle when that happens. So one of the things you also need to know about sp3 hybrids is that these are usually your single bonds. So pretty much everywhere you see a single bond, you're going to have an sp3 hybridized orbital. We also call these sigma bonds, okay? Sigma bonds. Now let's take a look at the other type of sp hybridized orbital, and that is the sp2 hybrid, where the s orbital mixes with only 2 of the p orbitals, and it leaves the other p orbital all alone, okay? So the other p orbital stays by itself, okay? I have noted on the image here with a red swirly where the sp hybridized orbitals are, the sp2 hybridized orbitals. And because we're mixing 3 orbitals, we're going to have an sp2 hybridized orbital there, sp2 hybridized orbital there, and an sp2 hybridized orbital there. And then the yellow area is the place where the p orbital that was not hybridized is all alone, okay? It's all alone. When sp2 hybridized orbitals form, we usually get 102 or 120 degree bond angle. And sp2 hybrids are known for making the double bonds, okay? The single bond of a double bond will occur on the sp hybridized part, so these red areas, and then the unhybridized p orbital will make the second bond to make it a double bond, okay? And for double bonds, they are made up of one single bond and then another pi bond, so we have a sigma and a pi bond in one, and we'll talk a little bit more about those later. The last type of hybridized orbital is the sp hybrid, where the s mix with only one of the p's, the s mixes with one of the p's to get an sp hybrid, and then 2 of the p orbitals are left alone, okay? When this happens, you're usually going to get a 180 degree bond angle because sp hybrids form straight lines, okay? Like this molecule of hydrocyanic acid, HCN up here. And sp hybrids are known for making the triple bonds, okay? The single bond of the triple bond will occur on the sp hybrid part, so this red swirly area. And then in the blue swirly areas, those represent the 2 p orbitals that did not get hybridized, and that's where the second and third bonds will come in. So in a triple bond, it's always made of one sigma bond and then 2 pi bonds. And again, we'll talk about sigmas and pi's a little bit later, okay? So again, just to reiterate, the s and p orbitals mix together so that we can describe how the atoms actually bond and overcome the discrepancy that we see in molecular orbital diagrams such as this one right here, okay? Stay tuned for the next video where we'll talk about actually assigning hybridization.